Okay, so sounds like particle kinematics, but it's different. So kinematics is describing motion without dealing with the causes of the motion. And we can think of the causes of the motion as force, mass, energy. We're moving on now to kinetics. And kinetics still involves kinematics. You're still using, and actually up here, basically what this is relationships between time, position vector, velocity vector, and acceleration vector. Kinetics is combining kinematics with the causes of the motion. So now we're going to start talking about mass and force and energy later on. For particle kinetics, if we're using a Newtonian approach, so a Newtonian force is one approach is one where you're dealing with forces, not energy. There's one equation of motion. And that's Newton's second law. I'll abbreviate that N2L. And by equation of motion, I mean an equation that relates the kinematics to the causes. So if you're given the causes of the motion, you can figure out what the thing is going to do. And Newton's second law says add up all the forces on the chosen body. I'll write the detailed meaning of each of these below. Add up all those forces, that's equal to the mass of the chosen body times the acceleration of the center of mass of the body. If you're dealing with particles, you're only dealing with the center of mass. But remember that, so like if you picture me as a rigid body doing this, at every instant, the acceleration of this fingertip is actually it's opposite, but it's definitely different than the acceleration of this fingertip. Okay. So if you add up all the forces acting on me as I do that, the sum of those forces can't equal the mass times acceleration of this and the mass times acceleration of this. They don't agree with each other. Okay. There's only one point on a body where that law holds, and that's at the center of mass. Okay. So F net, this is the sum of force vectors applied to the chosen body. m is the mass of the chosen body. And ACOM is the acceleration vector of the chosen body's center of mass. So this is going to be, I mean, this equation is going to come up in every problem that we do in this topic. You can see from the definitions of these quantities that specifying a chosen body is going to be a key part of this. So obviously, specifying, and being clear about what your chosen body is a key step. And so to be clear to ourselves, and I guess whoever is looking at our calculations, about what the chosen body is, what the boundaries of the chosen body are, we're going to draw free body diagrams. And you need to use a free body diagram, draw a free body diagram for every application of Newton's second law. Okay. So we're going to draw a free body diagram. We'll call that FBD.
This is our first free body diagram.
Yeah, in this class. Yep. For every application of Newton's second law. Okay, so here's what a free body diagram is. Different people have different, do these different ways, and probably most of those people are pretty sure that their way is the only way to do it. But here's how I want you to do it in this class. I want you to first draw a closed outline of the chosen body with no external objects and no internal details. No external objects, by the way, is the free and free body diagram. So we're taking the thing that we're isolating it, and that's the only thing that we're looking at. And anything in the environment, we're going to represent just simply as the forces that it applies to our chosen body, to our free body. So if you're doing a free body diagram of a person or a gingerbread man, there's a closed outline. This is not a closed outline. And the reason that that matters is because we're trying to be really clear about the boundary. So everything that happens inside the boundary is uninteresting to us. Everything that happens at the boundary is important. Okay, so if you if you draw just a stick figure like this, well, are we including, organs or whatever? Like, where the boundary is not clear. I mean, it's probably clear to you, or might be clear to you, but you want to give more details about where that boundary is. So what this says is we don't care about the forces of the blood acting on the arteries, or the forces of the arteries acting on the blood, or the forces of the teeth on each other, any of that stuff. All we care about are the forces that the stuff outside that boundary, the forces they apply to the boundary. Okay. And no external objects means don't do that. And you can do that, but that's not a free body diagram. Okay. Like you can draw, I think it's almost never the wrong step to draw more pictures of what's going on to get a sense of what's, to orient yourself to the problem. But your free body diagram should not have anything that is not your chosen object. Okay, so the grass there, it looks nice. I'm all for drawing grass, but not in the free body diagram, And then in addition to the closed outline, include all external loads acting on the chosen object. And I'm going to break this up into two possibilities. One is that you know the direction of the load. And loads, I'm going to think of this as a combination of forces and couples. Couples won't matter yet. We'll get to those when we talk about rigid bodies. When we're talking about particles, the only loads that matter are forces. If the force direction is known, then draw the force as an arrow in that direction, that known direction. And label that arrow with a scalar number or variable. So for example, if you're drawing a free body diagram of a car, okay, there's the closed outline. And then if it's being, if a force is being applied, it's this way. You draw the arrow in the direction that it's known. And then the variable associated with it is just the number. It's not a vector. Okay. What that is going to let us do is figure out how many variables we're introducing into the problem. Because what this is saying is take a unit vector in that direction and multiply it by that number. Okay. And so to represent this vector, even though a vector has 2 dimensions, we only have one unknown that we have to solve for. And by the way, if this t is negative, that means that we have a vector going in the opposite direction. Okay, so where I see this done wrong most often is when people draw weight force vectors. They'll draw a downward force and then write a negative mg on it. Okay, the downward is already the direction. If you multiply that then by a negative number, it means that gravity is going up, which you can't count on. Yes? Yes, it's fine to do that. Just know that that's what it does if it's a negative value. Yep. And the other possibility is if the force direction isn't known, then draw arrows in the directions of the coordinate axes. And label that with a vector variable or value. So if I use that car example again, let's say we're dealing with the force that's applied to the car by the ground at the front wheel. You can represent that like this and label it with a force F, or what I think is maybe more common. So on the left is the way I do it, but this is probably the way more people do it. So this is the component Fx, and this is the component Fy. But it means the same thing. In both cases, you can look at that and tell that there's two variables we need to solve for. Okay. So do we know that this force, that these force components are both going to be positive when we solve for them? No, that's just saying that if the number is positive, I mean, that's saying that each of these components, that's kind of the unit vector representing it. So if you do the calculations and Fx ends up being -5, then that says that you have a vector component with a magnitude 5 going in the negative x direction. Okay. So the signs in that case will just work out for themselves. So when you draw those, you want to draw those default component directions in the positive axis directions. Okay, let the signs work out on their own. All right. When we talk about a force applied to one body by another body. Oh no, wait, I need to say something before that. Ground yourself with this calming fact. The only forces acting on the chosen object are field forces that mainly just means gravity in almost, every case in this class. Um, but it also can mean magnetic fields, electric fields. If you're dealing with a field uh, that you have that's important, if you're in that application. Yep. No, that's a good question. So, okay, so of um, the meaning of a field force is it's the same thing if you remember conservative forces in physics one. Yeah, I mean, you might not remember in detail, but you probably remember hearing that term. But the idea of a conservative force or a field force is that if you know the location of the object, that's enough information to specify the force that's applied. Okay. Um, so gravity, if we're thinking of things as pretty much at the surface of the earth, like we always in all of our calculations, we're going to treat gravity as if it applies a force of mg downward. Okay, that's an approximation that's just assuming we're close to the surface of the earth. It gives good results anywhere from the lowest point below sea level to the top of Mount Everest. It gives pretty good results. But if you get out into orbit or whatever, it doesn't give good results anymore. But so ask yourself, so this stapler, okay, we know the mass of this stapler. If I tell you the location of this stapler, is that enough to know the force that gravity applies to it? And gravity is actually an extra simple case when we're using that approximation. I don't even have to tell you the location. And you know that the force is the mass times 9.81 down. Okay. And so gravity you can think of as it's a conservative force. You can think of it as a field. And the word field just means, what does it mean to, yeah, so like, yeah, a field of, let's think of a field of something, like a field of daisies, okay? A field of daisies, the idea is that wherever you go, there's a daisy there, okay? A field of forces, the idea is that these latent forces are just waiting there in space for the stapler to get there. And when the stapler gets there, then that force is already ready for it, kind of. Okay, that's what the word field comes from. You sort of follow what I mean? So, not all forces work that way. Uh, like friction force, is it enough for me to specify that this stapler is going to be at this point to know what the friction force is? No, because if it's sliding to that point this way, the friction force is that way. If it's sliding this direction, it's the other way. Okay, so most forces don't have that property where the location is enough information. Okay, but that's what field forces are. It's like a force waiting there for it. Gravity, magnetic field, electric field. Distributed loads just mean that the force is spread out over some area. So you can have a friction force that's a distributed load, but it's not a field force. Okay, that was too long an answer for sure. I'll probably go in later and edit out like half of the words, every other word. And then, so once you've dealt with the field forces, that's gravity, and then probably that's it, but maybe an electric field or a magnetic field or something like that. Then the only other thing that you have to deal with are contact forces. Between the surroundings and the boundary of the object. So in a complicated problem where you look at it and your brain sort of wants to freak out, just remind yourself that basically represent the gravity force, the weight force, and then represent the force wherever the surroundings contact the boundary. Boundary. And then you know you're done. It doesn't matter how complicated the problem is, that's all you're trying to do. Okay, so like if you have a problem, like you're asked to calculate this thing where this is mud, and then there's this pig stuck in the mud. And there's someone on the bank of the mud pit trying to pull the pig out with a rope. And this person, you can see the sweat. And this person is wanted for multiple parking violations. So there's like a police car trying to pull this guy away. And there's a bird on the pig. Thanks. And you know the idea. There's a helicopter sitting on the, waiting in case it needs to get deployed. Police helicopter. Let's stop there. What are the forces on the pig? Well, there's all this stuff going on that affects the forces on the pig. The police car is pulling on the guy. How hard the police car can pull is affected by the weight of the helicopter. How hard is the man pulling? That affects how hard the police car can pull. All this stuff is affecting how likely the pig is to get out of the mud. But all you have to do in the free body diagram is make sure that you represent the pig's weight, and then go around the boundary and look for objects that are in contact with the pig's boundary. So there's a force from the mud. There's a force from the bird. there's a force from the rope, and that's it. So the free body diagram is going to have 4 forces on it. A force from the mud, a weight force, and then force from the mud, the burden, and the rope. And all this other stuff, it affects, I'm not saying the other stuff going on doesn't affect the forces acting on the pig, but there's only those 4 forces acting on the pig, okay? So do you see how, like, in a crazy problem like this, that could be sort of a simplifying sort of touchstone? All you're doing is going weight and going around the boundary. That's better. Okay, so now for force vectors, we're going to use this double subscript naming convention. So this double subscript notation for force vectors. And this will also be true for couple vectors. Later on. And they're, the basic idea is that you just have this force is named by 2 subscripts, one that describes the chosen body and one that describes the thing that's applying the force. And you can do it in either order, as long as you know which order, as long as it makes sense to you, which subscript represents which. In this class, I'm going to use the subscript, and you should use this too. Force AB is the force vector on body A applied by body B. And I want to make sure that, so notice you can use this for vectors or vector components. But don't use this for forces with known directions. So what I mean is, in this example, so in this case where we have a car with a force magnitude P applied in this direction, don't write this as the force on the car by the cable or something, okay? Because that force has a known direction, and so we've drawn that arrow in some specific known direction, okay? If you use that double subscript notation with this, it'll end up messing up the way you think of Newton's third law and some other stuff, okay? So only use this for vectors and components of vectors. so Newton's third law. When I use this, I'll call it N3L. This is the one that says for every action, there's an equal and opposite reaction. But with that wording, it's pretty hard to use this law in a careful mathematical way. So for us, we can just think of the meaning this way. The force on body A by body B is negative force on body B by body A. So if you switch the subscripts, you have to switch the signs. Okay. That's the benefit of that double subscript notation. Well, we're not using that double subscript notation for forces with known directions. So how do you use Newton's third law with known directions? So that's just going to work like this. For forces, sorry, let's say for contact forces, with known directions, so let's say that we have body A here in contact with body B. Then a free body diagram of body A. That force has a known direction like that, and a magnitude R. And then a free body diagram of B has that same magnitude R, and you just draw the vector in the opposite direction. Notice though that, I mean, just to bring these two ways of doing it together, notice that, so this, if this is how we represent this force with a known direction, okay, you could also represent that in vector components based on that scalar R, and you could think of that whole vector as the force on A by B, and that's a vector. It's just that there's only one variable in there. It's not two unknowns, it's only one. And you could think of this one as the force on B by A. And if you switch the arrow direction like this, follow these rules, then those vectors are going to be equal and opposite. Okay, so I said what you do if you have forces with unknown directions. I said what you do if you have forces with known directions. There are three force types with known directions that we're going to deal with, besides gravity, I guess. I don't have a section on that, but gravity acts down. Magnitude is mg. So here are the three forces, the three, I guess, contact forces that we're going to have to deal with that have known directions. The first one is a pushing contact. The second one is a pulling contact. And you can think of this as being applied by a cable, even if there's no cable in the problem. You can always think of it as like there's a little invisible cable that things are being pulled by. And then the third one is friction. Okay, so the first one, pushing contact. The direction of that force is always perpendicular to the surface of contact. And toward the chosen body. So for example, if you have these two carts in contact with each other, let's say there's 500 newtons applied this way. Then a free body diagram of A has the weight, so I'll call that MA times G down. And now all we have to do is go around the boundary looking for contact with the surroundings. There's a pushing contact from the ground. The ground is pushing up on the wheel. So I'll call this, these are just variable names. You can call it whatever you want. I'm going to call it N for normal and A. There's really one at each of these two wheels, but since this is still particle stuff, really everything we're treating like it happens at the same point. And then there's a pushing contact from cart B. So again, just like with this normal force, that's perpendicular to the surface of contact toward the chosen body. So like that. And the free body diagram of B. There's a weight force of MB times G. There's a pushing contact from the ground, so that's perpendicular to the surface of contact toward the chosen body. So I'll call that NB. And if I just keep going around the boundary, now that 500 Newton force is applied to this one. It wasn't applied to the other one because it didn't act on its boundary. And then over here, there's a pushing contact, and Newton's third law says switch the direction, change the label. Switch the direction, keep the label the same. Don't change the label. Okay, I have 2 minutes to do this other one, and I really want to get to this point. So we'll do friction next time, but the second one is pulling contact. And you can always think of this as being done by a cable. And the rule for the direction of a pulling contact is parallel to the cable, away from the chosen body. So pushing was toward the chosen body, pulling is away. And so if you have a cable connected to the ceiling, and so let's call this body A. Then a free body diagram of A. There's a weight force of the mass times 9.81 meters per second squared. There's the 50 Newton force this way. And then the pulling force applied by that cable is parallel to the cable, away from the chosen body. And with cables, usually I label these with a capital T for tension. Again, that's just a variable name. And often we're going to use the fact that a cable's tension, that value T, is constant over the length of a cable. You can make that assumption if you have the following things. Well, the cable is weightless. And any pulleys that the cable passes over are frictionless and massless. Okay, so if you had to estimate in all the systems of pulleys and cables in the world, what fraction of them have weightless cables and frictionless and massless pulleys? Yeah, so none. It's an approximation, but it actually is a pretty useful approximation a lot of the time. So for now, we're going to make this assumption. Later on, I'll talk about how to introduce some of those things that could change this.